Everyone, welcome to our August colloquium. We're going to kick off today with a Bioenergy 101. Today, Heng Ji, a professor in computer science here at Illinois and a member of CABBI's conversion theme, will present a Bioenergy 101. Today, she will explain what image extraction is and how her team is using it to help propel CABBI research forward. And with that, I'll turn it over to Dr. Ji.
Thank you. And I need to click something here. Okay, cool. Okay, great. Nice meeting everyone. I think I saw many of you in the previous symposiums, but yeah, I'm a CS faculty. I have been working mostly with Hui Ming on a couple of CABBI projects, but I welcome any potential collaborations because I'm still feel like I'm so new to the bioengineering domain, but I have so many ideas related to AI, related to database construction. Would love to work with everyone here. Yeah, so I only have about 12 minutes talking about what is IE, information extraction. It's actually a very, very old topic. I have been working on this area for almost 20 years since I was an undergrad student. My first undergraduate thesis was on Chinese name tagging, so it's finding names from unstructured text. Yeah, so the goal of IE is trying to convert any unstructured data, either text, image, videos or speech into some structured format database, knowledge base, right? So I would like to use the general domain as an example because this is how really the field got developed. It was proposed initially by DARPA. It's a defense agency back in 1960s. So they got lots of messages, military messages. They want to quickly convert the most important information into some database for people to understand the situation. So given a sentence like this, someone got divorced from another person, and then there's a sue event going on. So from here, we want to construct knowledge base. You can also think of this as a knowledge graph. And there are two key events here: a sue, a divorce, and then two people are involved. Sorry, this is not a very pleasant event, but this is already much better than attack or arrest event, right? So two people are involved, and you can see there are two entities. They have if the person can be linked to an existing database like Wikipedia, we do anti-linking, right? Link that to the entry, and then there's a relation. There's a formal relation called spouse relation, and then there's also a co-reference resolution is trying to link the different dimensions of the same entity. Like this person is author, so author is mentioned linked to this person, right? So this is what we aim to do. And then you can see that in order to construct this graph or knowledge base, we need to perform a series of subtasks. So first of all, we need to identify all the mentions, noun phrases referring to the entity, and then we do co-reference resolution, group them together so we have the entity node. And then we need to do relation detection, try to figure out whether these two people are spouse or friends. And then we do event detection. So event detection has two things. One is we want to identify the word, which is called a trigger word. So here, born is a trigger word for this birth event, right? So we find the most indicative words or phrase indicate the event. And then we find all the entities who are participating or involved in the event. So for example, these two people, or maybe the time, place. And then for each entity, we identify the roles, like what kind of roles they play in the event, right? And then if there are two entities, they refer to the same one, then we do co-reference resolution, group them together. If there are two events also refer to the same event, then we also do co-reference resolution on the events, right? So that's the whole pipeline. It's a very complex task. And why we care, right? In the scientific domain, we do this a lot, right? Like we have millions of papers we need to read, and then we basically encode the information, we try to construct a knowledge graph, and then once we have the knowledge graph, a knowledge base, we can then do search, we can do question answering, we can do summarization. So yeah, we can do all kinds of interesting things. So this is a example that I did during pandemic, basically. So at the beginning of COVID, the crucial question at that time was like, what kind of drug can be repurposed to treat COVID, right? So no one knows the answer. But for biologists, we know the genes and the chemical entities that are related to COVID. And for the medical side, they do know what kind of other diseases are related to COVID, right? They belong to the same family. So on the right side are those the diseases, and then we also know their symptoms if they take any drug to treat that particular related disease, right? So what we can do is that we can read millions of papers, from the biology side, and then from the medical domain, and then we can connect them together. So we can see like which, for example, event like increased activity or decreased activity for this two drugs like L drug, B drug, which of them might cause more side effect, for example, for the related disease. So for example, I know nothing about these two drugs, but then if you look at the connections between the drug and the genes and the chemicals, then you can see that the B drug might cause more side effect just because there are more negative connections, right? So just based on this knowledge, I can recommend to the experts, maybe you should prioritize the drug L rather than B because L may cause fewer side effects. So imagine you have to read millions of papers to figure this out, right? This kind of structured database can save you a lot of time, right? Okay, so how are we going to do it? So in a nutshell, you basically read unstructured data, you kind of encode the meaning of every word. So for example, for people, we'll have the word vector, or you can do other ways to represent the meaning, and then you encode them. And then for your target task, for example, here, for every token, every word here, we first decide whether the word indicates event. For example, Q is the event for attack. And you also decide whether a word is a part of an entity, like 19 people is an entity, right? And then so that's node construction. And then when you construct a node, then you also look at the context to see whether there are other entities involved in the event. For example, when we see queued, we look for whether any other person, entity, or time or location is involved in the event, right? And then when you see for example, the 300, that's also a person entity. Then you also decide whether the 300 is a victim for injury event or not. So you're gradually basically scanning through this sequence. Whenever you find anything interesting, is a trigger for entity or event, you construct a node. And then when you construct a node, you look at the other neighboring nodes to see whether you can add the edge. So the edge can either be the participant for event or can be relation between two entities. So that's how you construct a graph from a unstructured sequence. And this sequence can be a sentence, can be a paragraph, can be a document, or can be a huge corpus, so multiple documents. Okay, so you can see this needs some supervision, right? Because we need ground truth labels for these nodes and edges in order to train the model. So in the past many years, right, so about 20 years, when people try different machine learning algorithms to train these kind of models, we start to see great development because of the continuous representation of the words. So, like 19 is not just a number, it has a vector. People and maybe women, or men, they have some semantic connection thanks to the word embedding representation, and also thanks to all these supervised methods. So we go from SVM to maximum entropy. You can see the progress here. And, also, whenever we have any supervised successful methods which is adopted. But as a result, actually, if over many, many years, we kind of narrow down the scope of the input. So we start from 1996, that was the first share task for IE. We start from the whole corpus. And then once we have maximum entropy model, we start to use maximum entropy to understand sentence level because, maximum entropy, the content cannot go beyond one sentence. And then when we have BioLSTM, we use BioLSTM, and then later, CRF and so on. So that's really becoming a problem because although the performance or quality of extraction becoming better and better, but then the scope becoming more and more narrow. So recently, this was Professor Jiawei Han's student, Zoe Li, when she was a PhD student here, she said, let's go back to the original task, which is corpus level or document level, i.e. So she proposed the first idea to use large language model. So the idea is that you take the document as content, and you take the template. Template means ontology, like what type of information you're looking for as additional content. And you let the large language model to continue talking about a story. So for example, here we're looking for who are involved in this transaction event. So basically, someone was selling something to another person. So we take that content, take the whole document as input. And then we know what kind of template we are looking for, right? A, sold something to B at what time and what place. Take that template also as additional content, and we let the model to fill in the template. So this is a very new idea because it's not a classification problem anymore. It's really about generation. So you want the larger model to continue telling a story to fill in the information. So that was a big breakthrough because the performance almost doubled compared to the performance from this paper before this paper. So that's about quality, and then and scope, and then in terms of domains. Over many years, 2 decades, 3 decades, we were only working on news, right? No one cares about scientific domain. But only recently we realized that's an issue because if you need to have a successful supervised model for 30 events, you need to annotate 500 news documents. That's very expensive. So how can we scale this up? So again, Zoe did this paper, have this work about 2 years ago. She tried to construct a gigantic ontology for events. This covered more than 3,400 types of events instead of 33 types of events. So the idea is that once we have this very big ontology, then you can do transfer learning across different types. So that's another breakthrough, basically cross domains. And then there's another direction is about go beyond text, right? So a lot of information, especially in scientific papers, the information comes from charts and figures rather than just text. So the same thing for news and social media. A lot of information comes from the images and videos. For example, if you only look at the caption, you won't be able to know the intent of this protest. So you need to understand this image. And then also more languages, like English has been the dominant language for many years, but a lot of information, especially when we care about, say, natural disasters in a local region, we want to understand all the languages, right? So we did a project that can understand 300 languages. So basically you can, for example, the earthquake place and also, which place need water, you can aggregate the information from all the local language messages. And then, as I said, cost was really huge problem. Over many years, the government spent a lot of time and money to annotate the ground truth. But the recent years, because of the large language model development, especially because of program language model. So program language model is basically you train some large language model from Python code, for example. So why that's useful for IE? Because you can then define the ontology, use the functions. So for example, I have one function for event called transportation, and I can define the entities I'm looking for as variables of this function. And then I can feed in the input document into the docstring, into comment, because code is naturally a semi-structured data. You have the structured code and you have the comments, right, docstring, written in natural language. So you can feed in the content into that comments. And then once you train this large Python code-based language model, then you can just generate this kind of information automatically. And you don't need a lot of examples. You probably only need 50 examples rather than 500 documents. Also, code LLM is much cleaner than natural language model because we only use those code that have 5-star from GitHub for training. And also you can inherit a class from another class, right? So that means once you have annotation for one type of event, you can transfer the training data to another event type that has lower resources. And then one natural question, honestly, a lot of us in the IE field feel like we are dinosaurs because, we only care about the structured data. Nowadays, people believe that they can do knowledge acquisition from a large language model. Everything's a sequence. So this really nice survey paper did an overview about the comparison. So from the comparison of all these models using LLM, not using LLM, there are two conclusions. One is that if you use LLM, then you can get much better performance if you use the same amount of training data. And if you also have very limited, 50 examples, you can already get a similar performance as compared to the previous model, which did not use LM, trained from 500 documents. So that's good news. But if you look at overall performance, end-to-end, we are now something, for general domain, we are, so end-to-end means that you have to have this perfect graph, then you get 1 credit, right? So for that performance, F-score, which is looking at precision real core, we only have something around 75%. So there's a lot of work to do to basically construct the perfect knowledge base. So I want to very briefly talk about what's the main challenge for scientific domain. So scientific domain, the biggest problem is that scientists are very verbose. You describe some simple idea using very complicated language. So for example, if we check the distance between a trigger, which is the indicative word for event, and the arguments, the entity involved in event, we have the typical sentence look like this, right? So you guys can understand what this is talking about. I don't understand, but basically they are far away, right? So if you look at the number of tokens, there are about 77 words on average between the trigger and the argument. If you look at news, there's only 56, right? And anyway, so you get the point. So there are two solutions for that. One is let's try to translate this kind of extremely long, complex sentence into something more understandable, more structured. So there's something called semantic parsing. Basically, they can translate every word, every concept into a semantic graph. So basically tell you the subject, object, who's doing what to whom, but no labels for the entity and events. So let's translate that into the semantic graph. And then let's translate the semantic graph into knowledge graph. So that's one solution. And another solution is that let's just teach the large model to be able to understand infinite lengths of content. So this was my student Chihan's last year's paper. So basically, he proposed that let's only pay attention to the beginning of the content and also local content. Let's take out everything in the middle, and that actually can extend generalizability to infinite length. Okay, so to conclude, I think we are now in a golden time to be able to remarry large graph construction or information extraction with the large models. So the idea is that once we have a lot of unstructured data, like papers, we can construct this kind of knowledge base, knowledge graph, and then we can feed this kind of symbolic knowledge back into LM to update LM's parametric knowledge. And then once we have better LM, we can use LM to do better extraction. So this will be the proposed knowledge life cycle. Yeah, so a couple of links. So I have a really nice class slides, and you can just read the first few slides. I don't teach this semester, but this was from last year. I think it's still up to date. And we have really nice workshop we are organizing. We are going to do it again. And in my slides, I will share. We have tons of papers and the systems you can play with. Okay, thank you. That's all. I think I have time for questions. Does anyone have questions?
Any questions?
I have a 3 hours version.